Ooh, all right. Oh, I've got presenter view. Awesome. This helps. I'm going to look downwards and try and use a microphone, and I'm really sorry if I screw that up. I also have 55 slides in 35 minutes, so some of these are going to be quick. If you really, really want to learn a lot about like how radio really works, you should go onto YouTube and watch the talk that was on before me that Justin gave, because he explained a bunch of useful stuff. I'm going to tell you about how to build radios in scenarios where you probably shouldn't, or at least in scenarios where maybe you don't have the proper equipment. I will start off by saying thank you to a bunch of people. This isn't all my own work. This isn't all, I didn't sit in a room and like make this all happen. Everyone on this list did something to contribute towards my presentation, and whether it be code or ideas or just feedback on things, or just like giving me a logic analyzer at like 7 o'clock the night before I had to run a demo. Thanks, Jared. This is me, but you can already see me, and as I said before, we have a lot of slides to get through, so here's some stuff I do, and that's my face. All right, hopefully I've caught up a little bit of time. I'm going to present 4 radios, and I don't have live demos because of, well, they never work. And so what I did, what I'm going to try and do is show a couple of videos, and I'm going to show some screenshots of something that Mike and I built. Almost everything, in fact, everything in here is open source code, so you can find it on the internet, and there's going to be a slide at the end that kind of points you towards some GitHub repositories. If you have any questions, you can always email me or find me on IRC, on Freenode, and things like that, and ask how I did these things. I will give a disclaimer that you should know what your local laws are, and you should generally obey them. I'm like really up for some civil disobedience, but like if you're going to go do time in your life, don't do it for having annoyed a ham radio operator. Like, do it for something worthwhile. Protest an obscure law or something. Like, don't get busted for transmitting on the wrong frequency. And also, like, you don't know what's being used for emergencies in your area and things like that. So seriously, like, don't do it. It's not very cool. So let's go with our first scenario. I play around a lot with microcontrollers. I build microcontroller breakout boards. I write software for them, and firmware. Pretty much, I'm assuming everyone in the room has done something with a microcontroller before, right? Now, a lot of these have all sorts of peripherals on them. They'll speak USB. They'll have high-speed serial interfaces. They'll have ADCs. They'll have DACs. And a lot of these things are like interesting ways that we can play around with the analog world. So there's a question of, like, if you look at something like a HackerF, it's got dual 20 megahertz analog to digital converters on it. Like, that's a relatively high-end part when we're talking about microcontrollers. It's a separate, discrete component. But can we take the ADC inside the microcontroller and do something useful with it? Specifically, do something radio-ish with it. So I'm sure a lot of people know, like, Betteridge's law of headlines. These scenario slides will have questions in them. This is the opposite to that, because if the answer is, can we do this? It wouldn't be in my presentation if the answer was no. So I present you Breadboard SDR, which is a microcontroller plus a solderless breadboard, and that's what we're going to call a radio now. If you did ham radio stuff in like the 70s, this circuit probably won't be all that surprising to you, but it is a 2-component radio. So this is my ham radio rig. I don't have a ham radio license, so it's receive only because, you know, got to be neighborly on the spectrum. But I understand, I'm a software guy normally, and I understand this is very much a hardware-themed conference, so I think it's only right that I show you a schematic for this. So here it is. Any questions? So essentially what we're able to do from the microcontroller is we're able to produce, we've got PLLs in there, we can produce clock signals. There's a clock signal for running the core, for running the USB, for running other parts of the peripherals inside that part. And we can bring those out to a pin, and then we use a single diode as a mixer, and so we have antenna and clock go in, they get mixed, and then we just measure the voltage across that resistor. And this gives us a sort of a series of samples that we then stream back to a host system, and through the magic of sort of GNU Radio and other software-defined radio platforms, we're able to kind of explore these values. So, as I previously said, I'm more a software guy than a hardware guy. So, like, you see my schematic being incredibly simple, and then like this is my software. Like, what we're doing here is we're taking some hardware that's kind of off the shelf and very simple, and we're pushing as much complexity into software as we can. And all of these are GNU Radio blocks, most of them written by people who were significantly smarter than I am. I don't actually know, I haven't even looked at how I'm doing for time, but let's quickly walk through this. We start off on the top left, and we're going to snake down to the bottom right. We read a file in, we convert data types, we filter our signal, we like power squelch it, and the only reason we power squelch it is so that it doesn't sound horrendous when people aren't transmitting. So we just sort of set a threshold and say we only want audio when we think there's a real signal. We throttle it because we don't want to burn our CPU, and that's only because we're reading from file. We correct our sample rate, and then we do a narrowband FM receiver. And like, there seem to be quite a few blocks there, but actually a big chunk of that is kind of reading in from file, getting it into the data format we want, making sure we're working at a rate that is going to make the audio not sound ridiculous, and making sure all our sample rates match across the thing. And once we've done that, we can just stream the audio out. Now, I don't have a live demo of this for two reasons. One is, again, I'm presenting from Hackaday's laptop and the time. The other is that to do this, we need someone with a ham radio license to come up with an HT and kind of do the thing. And I don't have a license, so I'm not going to do that, but I'm going to show you some screenshots from the flow graph. And essentially, the one on the left here is what it looks like when there's nothing really going on. And the one on the right, you can see in the top, there's just the audio out. So those are the two output blocks, the two GUI blocks at the side, and they're showing us the output of Mike's voice, and all he's saying is his call sign and discussing it. And so like we also save this to file, and so you can see it here. Now, it might be a leap to some of you for me to say this is FM modulated audio, but a really telltale sign here is that his radio puts out a pilot tone at the end of any transmission when he lets go of the button to kind of let you know that that's where the transmission was. And I'm going to step away from the microphone. That's it. Here and here. It's just a very, oh, can I do this on the screen? Oh, I can. Wait. Oh, computers, how do they work? So what you can see is this pilot tone here, and so like we know that's the transmission we received. We also know because we were able to listen to the audio, but you're not able to listen to the audio because I don't. Capturing videos in Linux with GNU Radio is like an unsolvable problem. But you can grab that flow graph and you can go build this thing yourself, and it doesn't have to be a great FET that you use. We use that because we produce it, and there are a bunch of them sat on my desk. But you can pick up anything that has like high-speed USB and an ADC of a reasonable speed and quality, and you can replicate this experiment and go build yourself a 2-component, 3-component, if you include the dev board, ham radio receiver, FM receiver. So our conclusion for this section is, if you're building a radio in software, you don't actually need the hardware. We can push that complexity from one side to the other. And that's one of the nice things about software-defined radio and digital signal processing, is that we can move that complexity into software that other people have written rather than hardware that we have to design. All right, scenario 2. So let's say we've got this microcontroller, and we've built a project out of it, and what we want to do is then send some data. And we can go buy those like RF modules from DigiKey, and you should absolutely buy those RF modules from DigiKey or Adafruit or whoever. Like, that's the proper way to do it. They're going to have like filters. Filters are good. They're going to have they're going to be targeted at the right bands. You're not going to find yourself transmitting on obscure frequencies. But like even if you overnight it, you have to wait 24 hours for it to arrive from DigiKey, right? And like, I don't know, I'm basically a millennial. I can't wait that long. So So what we're going to do is we're going to try and build a thing from a microcontroller that transmits data without having a radio module. So I'm going to call this a clock signal transmitter. This is not entirely novel. We've done it in a slightly different way, but the three things here. The top one is an on-off key transmitter. It's essentially turning on a signal, turning off a signal to light up an IoT light bulb. Mike Walters did that, and you can go find that. Ung Sui's Fontana was hacking, I think it was a VoIP phone, and finding a GPO line and toggling it to send a radio signal. And then the Raspberry Pi FM thing, which I'm sure almost everyone has seen, is transmitting FM audio from a GPO pin on Raspberry Pi. And those are all kind of fun, but we wanted to do FSK modulated data, mostly to be competitive with Mike Walters, because he's a good friend of mine, and it's fun to be competitive with him. So this is what it looks like. This is my radio. This is the Great Vet One. It's an NXP chip, and it's a breakout board for that we design and write the software for. And this is my carefully tuned antenna. So I should probably explain how. I mean, again, go back and see Justin's talk if you want to learn about proper things about antennas. But I'm going to give you my rule of thumb of how you calculate the antenna. What you do is you open up the box of jumper wires and you reach in and you pull out a wire, and then you plug it in, and you're done. And I've had a couple of conversations this weekend about minimum viable product, which is kind of a horrible phrase, but minimum viable hack. Pick a wire, transmit the wire. Did you receive it? Yeah, then you're done. You've got the right antenna. Did you not receive it? Well, let's try a different wire. Always suspect the wire and not your own code. That way madness lies. So this is a very, very simple setup as well. In the previous one, what I did, we used a clock signal to mix with the incoming signal through the diode. And what I'm going to do now is I'm going to use those clock signals from inside the microcontroller that I can transmit. I can sort of pipe out to an output pin. The microcontroller is reconfigurable. I can just say, hey, make this pin into a clock pin, and give me the clock. And so there are multiple clocks internal to this microcontroller. I don't really know how to use schematic drawing software, so this is my whiteboard. I should take Chris's course in using KiCad. So what I do is I take two internal PLLs, two internal clocks, one that's kind of spare and not being used for anything. It's an audio one, and the other is the one that runs the USB peripheral, and I just kind of turned off USB and said, I'm going to use this for something else. And I set one to be 315 megahertz and one to be 315.1 megahertz. And then the SCU here, you just think of as a switch. It's the system control unit. It's a pin multiplexer. It allows me to connect things inside the chip to things outside the chip. And it allows me to say, this clock signal, make it appear on this pin, or this clock signal, make it appear on this pin. And all I have to do is switch that backwards and forwards at the data rate that I want to transmit, and now I have two different frequencies being transmitted, and that, my friends, is frequency shift keying. So I'm really hopeful. I've got a little video in the next slide. What you need to watch out for, because it kind of happens, it's a very quick demo. What you need to watch out for is the orange flashing lights on my target device. I couldn't bring my target device here because, you'll see, it's a bit unwieldy. So I run the code, and there you go. You see my lights flash. And that is how I unlock my car when my key battery runs out. So now I'm going to take a little note here to talk about actual radios, because we all think about idealized radios and how's this thing going to work? How am I going to interact with the radio? You got to remember, the person designing the radio in your car wants you to be able to unlock your car. They don't want your car to stop unlocking just because your battery's a bit flat, or you're at a weird angle to it, or you held the keys at a weird angle, or something like that. These things are very, very forgiving. There's a huge tolerance there. So the frequency deviation of my car keys is 25 kilohertz. The frequency deviation of my transmitter, because it's a right pain to configure the PLLs more tightly than that, is 50 kilohertz. So we're already doing twice the frequency deviation. But I also was off the center frequency by 45 kilohertz. And actually, I managed to make this work at 316, so I was like 1 megahertz off where it should have been. And the car's like, yeah, no problem. Come on in. As long as you, like, the security is in the rolling code, it's not in the radio system. And I will happily have a very long conversation with people about the security of rolling codes. But essentially, like, if the thing's going to oscillate and it's going to emit, it's a radio. Like, you might think of this as, wow, 20 minutes. Let's pick up the pace. You might think of it as noise or interference or emissions, but like it's radio. Just because you don't think you're modulating it, or just because you don't think it's doing anything, transmitting information, doesn't mean it's not transmitting information. And if I can craft the noise or the emissions coming out of like your device, then I can send information. So like this piece of work came originally from looking at getting data out of air-gap networks, and this is an incredibly viable method. Okay, so we used an ADC earlier in the microcontroller, but like there are some authoritarian governments in the world who restrict the movement of analog to digital converters. I know, it's terrible, it's upsetting. Can we build one without? And just to prove that there are these like horrendous authoritarian regimes in the world, here's a piece of documentation from the US government about what you can and can't sell as an analog to digital converter. And the British government do the same, and most European governments do the same. And like, I can build an ADC in this country, but I can't move it across the border because, you know, security. I don't get it. So like, can we approximate an ADC? Like, some of us know how analog to digital converters work. Can we approximate one from other sources? Again, the answer is yes. So we've got GPIO pins. We've got digital inputs and outputs on a whole raft of microcontrollers. And we can read those pins at a certain rate. Now, earlier what we did is we took a very simple RF front end and used a decent ADC and a whole bunch of software to kind of make up for the fact that we had a very poor RF front end. What I'm going to do here is slightly the opposite. I'm going to take a relatively good RF front end, and I'm going to put it in front of a really, really low quality ADC. So this is an RF front end salvaged out of a VCR. We actually bought it on eBay because it turns out it's easier to get the tuner on eBay than it is to get a VCR on eBay because it's 2018 and no one told us. This is hooked up to a Great Fit, again, same. It's the platform I'm using for all of these demos. Like, it's pretty simple hookup. Most of it is 5-volt power, and the RF signal coming back, and then we've got like 2 pins for doing I2C configuration of the device. This used to be on some really early software-defined radios, and so Matt Ettus actually wrote code to configure the thing years and years ago, and we just pulled that code, like rewrote it in Python, and just fired it across at the thing, and it took our 315 megahertz signal and brought it down to 43.75. Now, I can sample the GPIO pins at 50 megahertz, and they're real samples, so I get 25 megahertz of bandwidth. I'm going to try and explain radio things now, and I'm going to watch Jared Boone cringe in the front row as I try it. So we're at 43 megahertz. I can sample 25 megahertz of bandwidth from like 0 to 25, and we've got 1 bit of dynamic range. Like, the signal is either 1 or 0, and we're going to need more than that. So I'm going to explain 2 concepts to you. Or I'm going to tell you I'm using 2 concepts, and you're going to Google them afterwards. Undersampling. So what happens with undersampling is you receive radio signals that are at a higher frequency than you should be able to receive using your sample rate, but what you end up with is like aliasing, so essentially the band is kind of, the RF band, radio bands folded on top of each other. We've used this in the past. Mike Osman and I used this to receive all Bluetooth channels simultaneously by intentionally aliasing them on top of each other. We're doing kind of the same thing here. We're just saying, like, we know the strongest signal in this kind of alias pattern is going to be the one we're looking for, because it's going to be me stood like a foot away from the receiver with my car keys. So we're going to see aliases, but we're going to ignore them because this is a very idealized, we did it in a lab, it's very small scale kind of thing. The second one is the second problem I have to fix is that 1-bit sample. So we can use something called oversample and decimate. what we're going to do is take a lot of bandwidth, a high sample rate, and at a very low sample, low dynamic range, and we're going to just take every pair of samples and average them. So you see these set of samples, we just average each one, and we end up with half as many samples, but we end up with some more dynamic range. And then we do the same thing again. We take each pair of these in turn, and we average them, and we get something. And now, having taken 16 samples, I'm down to 4, but I've got more dynamic range. You see more of a kind of wave pattern there. And this can be logically extrapolated much, much further, and so we can decimate by a much greater amount, and we can just keep repeating this process until we get to a point where we have significantly more dynamic range, but we have much less bandwidth. But this is kind of fine, because we can sample at 25 megahertz, and my car keys have a 50 kilohertz wide signal. So I can just keep going downwards for that. So I just find it amusing that we use it undersampling and oversampling at the same time. They are different techniques. There's no reason you can't, and I know that because we do. This is the simple bit of software. I don't have time to go through this, but I will happily explain this to anyone afterwards. But essentially, there's just a bunch of stuff that happens that includes decimation and there's this right here, which no one can see except me, I'm sure. It says decimation by 200. So we take a 20.4 megahertz signal, and we get a 102 kilohertz signal, which is plenty still to receive the car keys, which are 25 kilohertz deviation. And so some weird things happen when you sample at 1 bit. Your FFTs look strange, like those ones on the left, an awful lot, because you get these sort of weird effects. But after we've decimated, it looks a lot more like the FFT that we'd expect from a frequency shift keyed signal. And on the bottom, we can see this kind of plot of the time versus amplitude plot. And you can see some things kind of emerging, and that looks like there might be a signal there. There's some power there at least. And then finally, what we do is we do FSK demodulation on it. We do frequency demodulation. And what you can see here, where's my mouse? There it is. 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1. That's FSK modulated data. That is, if anyone's quick enough, you can get rolling code to unlock my car. Give it a try. And you can then go and feed that back into the previous radio and transmit and unlock my car. So 1 bit of dynamic range ought to be enough for anyone. This is false, but it's fun to play with. All right. Final radio. I will finish on time. I will not. Right, so Big Brother, which we call Mike Osman, has developed a frequency shifting, an antenna switching board. What we can do, there's a technique that I imagine a lot of amateur radio operators know about called pseudo-Doppler direction finding. There are various different methods for doing direction finding in radio. The interesting thing about Doppler or pseudo-Doppler, in Doppler you move an antenna, you just kind of rotate an antenna very quickly. In pseudo-Doppler, you have multiple separate antennas and you switch between them very quickly. This means that you get kind of instantaneous switches between them, but you lose some kind of granularity of position because you only have the 4 or 8 or whatever positions. So we built a board to do this, and we wrote some code to do direction finding. And at some point, this board was sat on Mike's desk, and so I took it. And I said, well, is there anything we can do to transmit with this board? And there was some discussion about, well, when we receive, what we're looking for is a phase shift in the way that sorry, I should skip ahead to say pseudo-Doppler direction finding. This is where you should go for the explanation of pseudo-Doppler direction finding. This is then Mike and Skylar presenting the work at Supercon earlier this year. But essentially, we're looking for a phase shift in the signal as we switch antennas, and we can use that to say if antenna A to B has a certain phase shift, and then B to C has no phase shift, we can work out an angle, and there is some maths you can do that will let you know roughly what direction the signal's coming from. The array isn't necessarily calibrated, so it will give you a dot, and then you have to try and work out which direction that dot is, but there's some kind of, you can configure that with a signal source, or you can move it around to try and get a better granularity. The board looks like this. It's an antenna switch, it's just a bunch of ports and some switching circuitry. And then when we switch between the antennas, we get a phase shift. So we can also do the same thing by having two different lengths of cable and having those two different lengths of cable be half a wavelength off from each other and hooked up to the same transmitting antenna. We can now change the length of the signal path. So instead of taking two discrete antennas which are a distance away from each other and saying the time of flight between these antennas, we're saying we've got one antenna and the two cables are different lengths to approximate that same time of flight. Is anyone still with me on this? Okay, a handful of people. Is anyone who doesn't have a ham radio license still with me on this? So what we use is two lengths of cable. This is basically how I work everything out, is drawing it and then holding cables up. But essentially, you've got a wave. These are the two cables. They start at the same place behind my hand, I promise you, and then they kind of finish at different lengths of the wave. So what you'll get, if you feed the same thing into both cables and you had two antennas right next to each other, they would transmit slightly out of phase. They'd be transmitting a different bit of the wave at the same time because it would reach them at a different time. And so we can also do this to hook them up to the same antenna and then switch back and forth between them. Now, we want to play around at 2.4 gigahertz because, again, I didn't have a ham license or anything, so I needed a cheap 2.4 gigahertz source. I really don't have time to go into this, but this is a Bluetooth dongle that we were able to turn into a 2.4 gigahertz source, so it will emit just a carrier wave in factory test mode, and we hooked up an SMA cable to it. Is this a video, or is this not a video? Okay, it's going to be a video. So this is our direction finding rig. It's a couple of antennas in it. This is Mike's laptop, evil big brother laptop, and he's running the direction finding code. I'm not transmitting yet, but that's my Bluetooth dongle hooked up to my antenna switching board. I have those two different lengths of cable hooked up. So I start transmitting in test mode, and you can see we get a blue dot that shows which direction from his receiver I am in. And then I just start switching backwards and forwards very rapidly between two different signal paths, and it completely throws off his code. Adding a phase shift circumvents pseudo-Doppler. That is a statement I'm willing to make and is not entirely true, but for some value of circumvents and some value of phase shift and some value of pseudo-Doppler. All right, how long do I have left? 7 minutes, okay. Oh, I think I can do this. Huh. I'm as surprised as you all are. Okay, so using the same idea, if we can use that phase shift and we can affect pseudo-Doppler, can we put a carrier wave in, switch between two different lengths, and get a phase shift signal out? Or can I put any other signal in? Can I take a thing that transmits an AM signal and add a covert phase shift keyed channel on top of that? Because the original receiver won't care that there's a phase shift. But my nefarious receiver will see the signal and say, I bet there's a phase shift there, and pull out the excess data. So can I do that? So something similar has been done before, which was playing around with different modulations in the same signal, specifically with PSK31. And doing in PSK31, you have to reduce your power level when you shift phase, but the receivers don't notice whether or not you're doing that. They just assume you're doing that to be a good neighborly person on the spectrum. And so what some people did was they varied their amplitude at the point that you're supposed to reduce your amplitude to transmit a secondary signal on top of a phase shift signal. And that was Sergey and Travis a few years back. I'm going to do something slightly different. So this is the Opera Cake board, which is our antenna switching board. That's another one of those Great FET boards on top. And this has different lengths. So all of these are a quarter wavelength off from each other. I'm actually going to use, at 2.4 gigahertz. I'm going to use two of these, and I'm going to produce a binary phase shift keyed signal. So if I kind of transmit a carrier wave in, and then I pull out, this is in Spectrum. It's an excellent tool if you want to do wireless reverse engineering. I highly recommend you look it up. But you can kind of highlight the plot that you see up at the top and do a phase demodulation, and we can see these kind of instantaneous phase shifts at various points, and they're happening kind of exactly when we expect because they're at regular intervals, and that's what these cursors are showing me. So I can produce a phase shift signal. I can put in a 2.4 gigahertz carrier wave from a Bluetooth dongle. So 2.4 gigahertz, PSK, and it turns out after some measurement I can switch at like just over 11 megahertz. Another thing to note is direct sequence spread spectrum is just code for very fast PSK. So a 1 megabit DSSS signal is with an 11-bit chip rate is an 11 megahertz PSK signal. So if I can transmit an 11 megahertz PSK signal, I can get out of it a 1 megabit DSSS signal. Does everybody see where I'm going with this? Using a Bluetooth dongle and some antenna switches, I can produce a Wi-Fi network that doesn't exist. So Wi-Fi beacon, thank you. Wi-Fi beacon, this is a demo which works over a range of this. Like, both Mike and I had our phones right next to the transmitter for this thing, and you got to like make sure you get in the gap between other networks using that, and like there's no power, and there's a lot of filtering. I promise there's a lot of filtering because this is noisy and messy. But we were both able to grab we set up a network called Is This Revolting or What? And we were able to transmit that using a Bluetooth dongle and a microcontroller and 2 antenna switches to change the length of path between the two. So an external modulator can produce a covert channel. How many? 3 minutes. That's actually, I'm ahead of time. Oh, just take questions for 3 minutes. Again, I want to thank all these people. A handful of them helped get the demos working when I attempted to run them in the lab or other places. Just inspiration about like covert channels or how you twiddle GPIO pins to transmit radio. And I said there will be some references. You can tweet at me and ask me questions, and I will try to answer them. You can find me around. I'll be the guy looking like this with his own face on his T-shirt. The GreatFet code is at the top URL. The HackerF code's at the second URL. All the hardware designs are in those 2 repositories. Almost all of the software's in those 2, although not. I didn't encode the Wi-Fi network in firmware and upload that yet. I'm happy to talk to people about how to do it, but it seems kind of unneighborly to actually like just put that code up there because it's a bit messy and really like kind of nasty on the spectrum, and I don't want to do that because I don't want to do prison time for upsetting ham radio operators. That's it. I'm done. Thank you very much for listening, and I'll be around to answer questions.